Welcome back to The Explainer. Have you ever wondered what's really going on inside a machine learning model? I mean, deep down? Well, today we're going to pull back the curtain and build one from the ground up, using nothing but the raw power of NumPy.
You know, we use these incredible tools like PyTorch and TensorFlow, and honestly, they can feel like total magic. They're like these black boxes where we put data in, tell them to learn, and somehow they do. But what is actually happening in there? Let's dive in and really see what's going on under the hood.
And that quote right there, that's our mission for today. We are going to build a simple but a totally functional machine learning model from scratch. We're only going to use one library. No magic, just the pure core logic.
Okay, so let's start with our foundational tool. Before we can build anything, we have to understand why NumPy is basically the engine behind almost all of modern data science and machine learning in Python. The secret really lies in its architecture. Just look at this comparison. A standard Python list over on the left, it's kind of like having a bunch of sticky notes pointing to where your data is stored all over your computer's memory. It's scattered. But a NumPy array on the right stores all the data in one single continuous block. This makes grabbing that data incredibly fast. And because every element is the same type, NumPy can use super optimized C code instead of those much slower Python loops.
And this right here is the core concept that makes it all possible: vectorization. Imagine you've got 1,000,000 numbers, and you need to double every single one. In normal Python, you'd have to write a loop to go through them one by one by one. With NumPy, you just say, hey, multiply this whole array by 2. That's it. One command, and boom, it's done. At lightning speed, all thanks to that C code running behind the scenes.
And what's really wild is just how big that performance difference is. I mean, look at this. For a simple multiplication on 1,000,000 elements, NumPy isn't just a little bit faster, it's over 40 times faster. This isn't just an improvement, this is the kind of speed that makes modern machine learning even possible.
So now that we have our super powerful tool, let's set up our project. We're going to build a linear regressor from the ground up to find the line of best fit through a set of data points.
Our goal here is pretty simple. We're going to create some of our own data, about 200 points that kind of sort of follow a straight line, but we'll throw in a little bit of random scatter to make it feel more realistic. Then our job is to get our model to find the one single best line that describes all of this data.
So here's the blueprint. Our model is basically just trying to figure out the classic equation for a line, y equals mx plus b. But in machine learning, we just use different letters. We call m a weight and b a bias. So our model takes an input, x, multiplies it by a weight, adds a bias, and that gives us our prediction, which we call y hat. Then the last step is to measure just how far off that prediction was from the real data.
Okay, let's break down that first part. In machine learning, this is called the forward pass. This is where our model takes its best guess and then has to take a hard look at its own performance. So how does it make a prediction, and maybe more importantly, how does it measure its own failure?
It's a really straightforward three-step process. You can see it right here. First, we just combine our inputs and whatever our current weights are. For us, that just means plugging our data into the line equation. Second, that gives us our prediction, our y hat. And third, and this is absolutely the most critical part, we measure the difference between our prediction and the actual real data points. And we use a specific formula for this, called the sum squared error, or SSE. For every single one of our data points, we find the difference between our guess and the real value, we square it, and then we add them all up. Now, squaring the error is super important, and make sure that we treat being too high and too low the same way, and it means that really big errors get penalized a lot more. This gives us one single number that tells us just how badly our model is doing, and our goal is to make this number as tiny as possible.
And well, you can see it right here. When we start with just random weights for our slope and our intercept, our line is nowhere near the data. It's a complete guess, and our SSE value is huge. So now comes the fun part. How do we actually teach the model to fix this? This brings us to the absolute heart of machine learning, the backward pass, also known as backpropagation. This is how the model analyzes its own mistakes and figures out exactly how to correct them. This is how it actually learns. So the core idea here comes straight from calculus. We calculate the derivative of our error with respect to each of our weights. Now don't worry if that sounds intimidating. All it really does is give us something called a gradient. You can think of this gradient as a perfect little roadmap. For each of our weights, it points in the direction that will make the error go up the fastest. So, to make the error go down, we just need to go in the exact opposite direction.
So the whole process is beautifully simple, as you can see in these two steps.
First, we calculate those gradients. That's our roadmap. Second, we update our weights by taking a tiny little step in the opposite direction of that gradient. If the gradient tells us this way and makes the error go up, we just go the other way. This simple but incredibly powerful process is called gradient descent.
Okay, let's put it all together now. The training process is really just a loop. We do a forward pass to make a prediction, then a backward pass to figure out how to improve, and then we update our weights. And we just repeat this cycle over and over and over again. Each full cycle is called an epoch. So, at the very beginning, epoch 0, our line is just a random guess. As you can see, the error is really high. Now what's so cool is what happens next, after just a few updates. After 100 trips through this loop, that's 100 epochs, just look at that. The line on the graph has rotated and shifted itself, moving so much closer to the center of our data. The model is actually using the information from its past mistakes to get better. It's learning. And then, by the time we get to epoch 300, the line has pretty much settled in. It's converged. It has found the best possible slope and intercept to describe the relationship in our data. It has learned.
This whole thing just brilliantly illustrates the process of iterative refinement. We start out with a really poor fit and a high error, but through these repeated cycles of predicting and correcting, the fit gets good and then it becomes optimal, as the error drops from high to medium all the way down to low. This is the heart and soul of how most machine learning models learn to do what they do.
And we can also track this progress with numbers. This plot here shows the SSE value at every single epoch. You can see this really steep drop at the beginning as the model makes big, obvious corrections, and then it slowly flattens out as it fine-tunes the fit. This steady downward slope is the proof that our gradient descent approach is working, that it's successfully minimizing the error.
So that's really it. The magic of machine learning, it isn't really magic at all. It's just a simple loop, guess, check your error, and adjust. By understanding these first principles, you're not just a user of a tool anymore. You actually understand the engine. So, the only question left is, what are you going to build with it?